In this lecture, we're going to introduce the idea of a partial derivative. This allows us to define the rate of change of a function of several variables. Now, we've already seen that functions of several variables come up all the time in engineering and the sciences. And the partial derivative extends the idea of an ordinary derivative that you've already seen in your first year and high school courses that defines the rate of change of a function of a single variable. A partial derivative allows us to do the same thing for functions of many variables. So let's take a look at the definition of that. So I've given you the definition here in the boxed text for the derivative, partial derivative, of a function z of x and y with respect to x and with respect to y. Obviously, I can define the partial derivative in either x or y, and those are given by these two formulae here. You notice that we've introduced a slightly new symbol for derivatives. It's got a little curly d instead of the normal d. That's to indicate that the function z depends on both x and y. I've also specified which variable I'm taking the derivative of in the bottom. So this is the partial derivative with respect to x and the partial derivative with respect to y. Now we're going to see that it's going to be very convenient to introduce a shorthand notation, z with a little subscript x to indicate the partial derivative with respect to x, and z with a little subscript y to indicate that it's the partial derivative with respect to y. Now the definitions of those partial derivatives are given here, and they look a lot like what you've seen already in your first year courses. But what we're going to see is that in practice it's a lot easier to just treat the other variable like it's a constant. I'll demonstrate that now in an example. So looking at example 1. So here we have a function z again. Again, it's a function of both x and y. Z is equal to x squared plus y to the power of 5 plus 7. And we want to calculate the partial derivative of this with respect to x and the partial derivative with respect to y. Again, the way that we're going to actually do this is by picking the variable we're going to take the derivative with respect to. So let's say we're going to take the derivative with respect to x first. So that's the partial derivative with respect to x of z. Again, notice that I'm using the curly d notation to indicate that this is a partial derivative. And what we do is very simple. Every time we come across a function of x, we take its derivative just like we would with ordinary derivatives. So the derivative of x squared is 2x. And every time we come across a function that depends on y, we treat it like it's a constant. So in this case, y to the power of 5, y is a constant, so of course y to the power of 5 is a constant. The derivative of a constant is simply 0. So this becomes 0. That's the derivative of y to the power of 5 with respect to x. The last piece here is 7 plus 7, so that's a constant again, so the derivative of a constant is 0. So we see that the partial derivative of z with respect to x is 2x plus 0, which is equal to 2x. Again, notice that all we've done here is we've taken the derivative just treating all of the other variables as if they were constants, as if they were numbers. Let's try the same thing now for the partial derivative of z with respect to y. So again, I'm going to use the curly d notation to indicate that I'm taking the partial derivative, dz dy, is equal to, well, the first part of my function is x squared. That's a function only of x. And since I'm taking the partial derivative with respect to y, I treat that like it's a constant. So the derivative of a constant is 0. The next part is y to the power of 5. I'm taking the partial derivative with respect to y this time. So I have to take the derivative and get 5y to the power of 4. The last bit is plus 7. Again, that's a constant, and the derivative of a constant is equal to 0. So I'm left with 5y to the power of 4. So again, the thing to remember here with partial derivatives is that they behave just like ordinary derivatives that treat all of the other variables, that is the variables that I'm not taking the derivative with respect to, it treats all of those variables as if they were constants. Let's look at the next example. So what we're going to find here is that when we're taking partial derivatives, lots of the rules for ordinary derivatives actually just carry straight over. That includes all of the rules for the derivatives of different functions, basic fundamental functions that you've learned, and also things like the product rule and the quotient rule. The chain rule we'll actually take up in the next lecture. So in example 2 here, we have a slightly more complicated looking function. Z is equal to x cubed times y squared plus cosine pi x plus 3y minus 2. The first thing we want to do is calculate what the function is at the point 1, 2. So x is equal to 1, y is equal to 2. Okay, so the value of our function is, substituting in x is equal to 1, y is equal to 2. I get 1 cubed times 2 squared plus cosine of pi times 1, that's cosine of pi, plus 3 times 2 minus 2. So I get 4 plus cosine of pi is minus 1 plus 6 minus 2, and that is equal to 7. That's the value of our function of two variables at the point x is equal to 1, y is equal to 2. As usual, we just substitute in the values of x and y. Now we want to calculate what the derivative of the function is in the x direction, or as we put it in the question, the rate of change of f in the x direction. So the rate of change of f in the x direction is given by the partial derivative of f with respect to x. And we're going to have to calculate this, of course, first for all x and y, and then we're going to substitute in our values of x and y. So what is df dx? Well, we're going to calculate the partial derivative of this complicated function up here, x cubed y squared plus cosine pi x plus 3y minus 2. But we're going to treat y like it's a constant. So let's take a look at the first term. We've got x cubed y squared. Y is a constant. And whenever I have a constant multiplying a function of x, that constant just comes out the front. Right? I don't take the derivative of it. I'm left with x cubed, and the derivative of x cubed is 3x squared. The next piece is cosine pi x. There's no y in there. I'm taking the derivative with respect to x. So the derivative of cosine of pi x will be, pull out the pi, minus pi sine pi x. The next piece is plus 3y. That's a function only of y. The derivative of that with respect to x will treat y like it's a constant. So the derivative of a constant is 0. And again, the last piece, minus 2, is also a constant. So the derivative of that will be 0. So what are we left with here? We've got 3x squared y squared minus pi sine pi x and that's our partial derivative of f with respect to x. We're not quite done yet, of course. Now we have to go back and substitute in what x and y actually are here. So the partial derivative of f with respect to x evaluated at x is equal to 1 and y is equal to 2. Let's just substitute in what x is and substitute in what y is. Minus pi times the sine of pi times x is equal to pi, so the sine of pi is equal to 0. And we're left with 3 times 2 squared, which is 12. And that's our derivative of f with respect to x at the point 1, 2. Of course, we're not constrained to just functions of x and y. There's nothing particularly special about those letters in the alphabet. We can use different letters. So let's take a look at an example that involves different letters or different variables. So example 3, we have a function w of u and v. Again, you notice that it involves terms that are products or combined functions of u and v. And we want to find the partial derivative of w with respect to u and the partial derivative of w with respect to v. So, dw du is going to be equal to, the first term there is u cubed v to the power of 4. So we treat v like it's a constant, so it comes out the front. The derivative of u cubed with respect to u is 3u squared. The next term involves only a function of v, and the derivative of that with respect to u will of course be a constant. The derivative will be 0. And so we're left with the partial derivative of w with respect to u is 3u squared v to the power of 4. Now let's look at the partial derivative of w with respect to v. Again, I've got that mixed term, u cubed v to the power of 4. So I'm going to treat u cubed like it's a constant, because this is a partial derivative with respect to v. The derivative of v to the power of 4 is 4v to the 3. And now I have the hyperbolic sign of v to the power of 9. Now, we're going to need to use the chain rule here for this. Because this is a function only of v, I can use the chain rule that we learned for ordinary derivatives. And so I need to have multiplied the derivative of v to the power of 9, so that's 9v to the power of 8, multiplied by the derivative of the hyperbolic sign, or sinh. So that's cosh, hyperbolic cosine of v to the power of 9. So my partial derivative of w with respect to v, let's write that out neatly, is equal to 4u cubed v to the power of 3 plus 9 v to the power of 8 hyperbolic cosine v to the power of 9. And I'll just put brackets around that to make it clear. Okay, so if at this point you're feeling a little bit rusty on your ordinary differentiation, I encourage you to go back to your first year notes and revise those, especially the use of the chain rule and derivatives of fundamental functions. We're going to use those again and again. As you see, taking partial derivatives of functions of many variables basically involves taking lots of ordinary derivatives of functions with one variable, treating all other variables as constants. So you need to be strong on that. Let's take a look at a fourth example here. If you like, you can pause the video at this point and try this example yourself and then check your answer against mine. In this case, we have a function z of x and y. I want to find the partial derivative with respect to x and the partial derivative with respect to y. Let's try the partial derivative with respect to x first. What I'm going to do here is I'm actually going to write this out in terms of the different pieces. So I'm going to write a sort of partial derivative with respect to x and then a bracket of my function e to the 7y divided by x cubed plus 1. Okay, so you can see I've just rewritten the function z explicitly there inside of brackets. And you can see that the numerator of this fraction, the top part, is just a function of y. Because it's a function of y and this is a partial derivative with respect to x, again, we treat it like it's a constant, so it comes outside of the brackets. It's not affected by the partial derivative. So that becomes e to the power of 7y partial derivative with respect to x, and then inside brackets what I have left is x cubed plus 1 to the power of minus 1, if you like. Okay. So now we have to take the derivative of this function 1 over x cubed plus 1 with respect to x. That's a function of x, and I'm taking the derivative with respect to x. So again, I can use the chain rule. I'm going to get minus x cubed plus 1 to the power of minus 2. Let's put a big bracket around that just to indicate that it's not subtraction, it's actually multiplication. And I'm multiplying that by the derivative of the denominator, by the derivative of x cubed plus 1. And that's going to be given by 3x squared. So that's looking a little messy. Let's tidy it up. We have e to the 7y. I have a minus out the front. I have a 3x squared. And I'm dividing all of that by x cubed plus 1 all squared. So that's the partial derivative with respect to x. Now let's do the same thing for the partial derivative with respect to y. Again, I'm going to write this out as the partial derivative of this whole function z, so that's e to the 7y all over x cubed plus 1. Again, you notice that this is a function of y over a function of x. The function of x can be treated like a constant for this partial derivative, and so it will come out the front unaffected by the partial derivative. That leaves me with the partial derivative of e to the 7y with respect to y. And that's going to be equal to seven e to the 7y. And that's our solution. Now we've only just looked at how we find partial derivatives of functions without really thinking about what that actually means. And to understand what partial derivatives mean, to interpret them, we're going to have to first of all look at what functions of several variables look like in 3 dimensions. Now we've already seen that a function of one variable can be thought of as a curve in 2 dimensions. So y is equal to f of x can be thought of as a function in the xy plane. Now, in exactly the same way, a function of two variables, z is equal to f of x and y, can be thought of as a surface in 3 dimensions. To illustrate that, let's look at a couple of examples. So the first example here, example 5, part A, has a function 3x plus 4y plus 6z, and that's equal to 12. So you see that this is actually an equation. It's a relationship between a function of x, y, and z on the left-hand side and a number on the right-hand side. So that's going to be a surface in the x, y, z plane. In fact, this is going to be a plane. It's going to be a plane if it has a functional form as follows. If it looks like ax plus by plus cz equals to d. If I have an equation that looks like that, then I know I'm dealing with a plane. So let's put that in a box. Okay, so how do I draw what that plane looks like? Well, I know that any plane is going to be defined by any 3 points on that plane, as long as those 3 points aren't in a line, as long as they're not collinear. So all I need to draw this plane is to find 3 points on the plane. Now I could pick any 3 points as long as they satisfy the equation 3x plus 4y plus 6z equals to 12. That is, I could pick values of x, y, and z and check to make sure that they fit the function, the equation. If they do, I know it's on the plane, and that is a point. That seems a little haphazard, however, so what I'm going to do is be a little bit more systematic about it. I'm going to look for 3 very special points on this plane. I'm going to look for the intercepts of this plane with each of the axes, the x-axis, the y-axis, and the z-axis, which I've drawn here in this coordinate axis. So what do I mean by the intercepts? By that I mean when y is equal to z is equal to 0, if I substitute those values of y equals to z equals to 0 into my expression, I get 3x plus 0 equals to 12, which gives me that x is equal to 4. In other words, that gives me a point. X is equal to 4, y is equal to 0, z is equal to 0. That's a point on the x-axis that I can draw. Let's put it in. This is the point x is equal to 4, y is equal to 0, z is equal to 0. That's one of the points on my plane. Let's find the y-intercept by looking for the point which has x equals to 0 and z is equal to 0. So I'm going to make x equals to 0 and z equals to 0. Substitute that into my equation. 3x, so 0, plus 4y plus 6z, so equals to 0, equals to 12. I can solve that to find y equals to 3. And that gives me a new point. X is equal to 0, y is equal to 3, z is equal to 0, another point, and that's going to be a point on the y-axis. So let's put that point in. That's the point x equals to 0, y is equal to 3, z is equal to 0. Okay, so our last point is going to be where x is equal to 0 and y is equal to 0. Substituting that into my original equation gives me 6z is equal to 12, which implies that z is equal to 2. And that gives me my third point, which is x is equal to 0, y is equal to 0, and z is equal to 2. So now I have 3 points on this coordinate axis. I can now connect those points to draw my plane. And obviously that plane extends in every direction infinitely far. Okay, let's look at the next example. X squared plus y squared plus z is equal to 25. You see that that is of the form x squared plus y squared plus z squared is equal to r squared. And that's the equation for a sphere. So this is a sphere of radius r. R here is equal to 5. So this is a sphere of radius 5. And it's a sphere that's centered on the origin. So let's draw what that looks like. And let's draw a little line to indicate that this has radius 5. All right, next example. Example C. We've got x squared plus y squared is equal to 9. And you notice that that looks like the equation for a circle. Indeed, it would be the equation for a circle if we were only dealing with 2 dimensions here. It would be the equation of a circle with radius r is equal to 3. But we're not dealing with just 2 dimensions here, we're dealing with 3 dimensions. That third dimension, z, doesn't appear in the equation. And whenever that happens, whenever one of my variables doesn't appear in the equation for the surface, what that means is that this is true for all values of that variable. It's true for every possible value of z. Or to put that another way, whatever shape I make here is going to be infinitely extended in the z direction. And that's a very important rule to remember here. If ever I have an equation for a surface, but one of the variables is missing from that equation, what it means is that it's true for all values of that variable, and then what I do is I extend that shape infinitely in that direction. So in this case, instead of just having a circle, I've got a circle that's extended infinitely in the z direction. In other words, I've got a cylinder. So I've got a circle again of radius 3, but it's true for all values of z, so it becomes an infinitely long cylinder. And let's just indicate that this is a cylinder of radius r is equal to 3. As such. So that's again an important rule. If one of the variables is missing from the equation, it means that my shape is going to be extended infinitely in that direction. Another important rule to remember is if I have a function of the form shown here in example D, z is equal to 3 times the square root of x squared plus y squared. You notice that x and y only appear in the combination x squared plus y squared. And of course, x squared plus y squared, that's the equation for radius or distance. So what that means is that the particular values of x and y don't matter. All that matters is the distance from the origin, or the distance from the z-axis. So what that means is that my function, my surface, is actually going to be a surface of rotation. In other words, it's going to look the same no matter how I rotate it about the xy plane. So what do I mean by that? Well, let's replace the function x squared plus y squared with an r squared and see what that would look like. So again, I'm going to replace the combination x squared plus y squared with r squared. That means that my function z is actually not really a function of x and y at all. It's really a function of r, just one variable. So it's just equal to 3 times r. So I could almost imagine drawing this not in the x, y, z 3 dimensions. I could imagine drawing it in just z and r. Let's draw what that would look like. So that's z is equal to 3r. That would just correspond to a straight line with a slope of 3. But of course, r here is a radius of my surface of rotation, so it's rotated in the xy plane. So what I need to do is I need to take this tilted line and rotate it completely in 360 degrees. What that's going to give me is a cone. So it's perfectly rotationally symmetric. It's got a slope of 3. And you notice also that I've only drawn it in the positive z quadrant. I've only drawn it in the for positive z values. I haven't drawn it further down in the negative z value. And the reason for that, of course, is when I look at the equation, z is equal to 3 square root of x squared plus y squared, the square root is always going to give me the positive number. So I can only ever get positive values of z out of this. So this is not just defined for negative values of z, this surface. So again, the thing to remember in this example is that we have a function here that involves x and y, but only in the combination x squared plus y squared. So that means that this is actually a surface of rotation, and whatever surface I have is going to be symmetric when I rotate it about the z-axis, or rotate it in the xy plane. Let's take a look at another example of a surface of rotation. Example E, z is equal to x squared plus y squared. Again, notice here that I've got something that can be rewritten just as a function of r, where r is equal to the square root of x squared plus y squared. So this means that this is a surface of rotation. Let's draw what this surface of rotation would look like if I only looked in the ZR plane. So my function this time is z is equal to r squared. That would be a quadratic function. It looks like that. This is the function, if you like, pressed into just the ZR plane. What would happen now if I took that function and rotated it 360 degrees? Well, what I'd end up with is a paraboloid. So again, that's rotated 360 degrees. And again, it's only defined for positive values of z. I don't define it for negative values of z because I can't get negative values of z out of that expression. Okay, so the last example here, example F, looks a lot like our example E. In fact, it's exactly the same, except that I've moved around some of the variables. X, Y, and Z have now become Z, Y, and X. So let's compare that with the example I've just done. So we just did, so compare with the example we just did, z is equal to x squared plus y squared. And you see that they're actually exactly the same thing if I just relabel my variables. So that is, if I replace z with x, if I replace x with y, and I replace y with z, then I end up getting this new expression, x is equal to y squared plus z squared. What that means is that I can take my coordinate axis that I've drawn here and relabel the axes. So instead of z, I'm going to write this as x. Instead of x, I'm going to write this as y. And instead of y, I'm going to write this as z. So I've just relabeled my axes here. And under this relabeling, my surface looks the same. So again, I have a paraboloid in 3 dimensions. It's rotationally symmetric. That is, I'm now rotating it, but in this case, I'm rotating about the x-axis instead of the z-axis. I'm rotating in the yz plane. So you see that in this case, I didn't need to worry about trying to rotate my coordinate axes and trying to draw some complicated shape in 3 dimensions. I already know what this shape looks like. All I needed to do was relabel the axes. However, I have to take a little bit of care when I relabel axes like that. I need to make sure that the handedness of my coordinate system is the same. Now, what I mean by that is my coordinate system should be a right-handed coordinate system. If I was to hold up my right hand, I could label my axes x, y, and z. X, y, z. Right? If I want to relabel those axes, I have to maintain the order x, y, z. X, Y, Z. So if I want to relabel them as X, Y, Z, I can, or I can relabel them X, Y, Z. Another way to remember that is to draw a little circle here, a little cycle. So I can relabel Z going to X, X going to Y, and Y going to Z. I can go in that direction. As long as I maintain the order, that's fine. So that's something to bear in mind when you're dealing with sketching functions in 3 dimensions. We need to make sure that we're dealing with a right-handed coordinate system, one that preserves that handedness, x, y, z. Okay, we're now ready to try and understand what partial derivatives actually mean in terms of their geometric significance. So remember that for functions of one variable, y is equal to f of x, for example, I could interpret the ordinary derivative, dy dx, as the slope of my function. So you learned that in first year in high school. Now for partial derivatives, for functions of more than one variables, for example, for z is equal to f of x and y, the way that we're going to interpret the partial derivative of z with respect to x and the partial derivative of z with respect to y is as the slope of my function, but in a particular direction. So the partial derivative of z with respect to x is equal to the slope, the instantaneous slope of my function f of x and y, but in the x direction. Likewise, the partial derivative of z with respect to y can be thought of as the slope of fxy in the y direction. So let me show you what I mean by that. Let's go back to one of our examples, example E, which was the case, example 5e. That was our paraboloid case when we had z is equal to x squared plus y squared. Let's ask ourselves, what's the slope of this function in the x direction? The way that we're going to try and answer that question is by looking at different values of y. So for example, let's start off by looking at y is equal to 0. What does my function look like in that case? When y is equal to 0, my function z is equal to x squared plus 0. That's now just a function of x only, so I can draw it in just 2 dimensions. It's going to be a simple parabola, as we've seen. I could ask now, what's the slope of this function? Well, it's simply going to be the ordinary derivative. So the slope is going to be the derivative with respect to x, which is going to be, well, the derivative of x squared is 2x. So the derivative of this function is 2x. It changes with x, but at a particular value. For example, x is equal to 1. The slope here will be given by 2 times 1, it's equal to 2. Now that's the case when y is equal to 0. I can repeat this exercise for another value of y. Let's try y is equal to 1. So y is equal to 1. In that case, my function z is equal to, again, x squared plus y squared, x squared, but this time I'm replacing y with 1, so I get 1 squared, I get 1. So my function is z is equal to x squared plus 1. That's going to be, again, a parabola, except this time it doesn't go through the value z is equal to 1, z is equal to 0. Instead, it cuts through z is equal to 1 at x is equal to 0. And I can again calculate the slope of this function of x. So that's the derivative of z with respect to x. And z now is given by x squared plus 1. The derivative of that is 2x. So you see that the derivative is exactly the same. Again, I can ask what is the slope at a particular point. X is equal to 1. Substituting it into that expression gives me slope equals to 2 times 1 is 2. So you notice that in both of these examples that I've given here, I've ended up with the same expression for the slope. dz dx is equal to 2x, and the same value of the slope at a particular value of x. And that's when I've taken y is equal to 0 or y is equal to 1. In each of these cases, I just substituted in a constant value of y, and that didn't affect the derivative, so it didn't affect the slope. That's the key point here about partial derivatives. If I treat a variable like a constant, it can't affect the slope. So I could do this for any possible value of y. Let's call it y is equal to some constant a. That gives me z is equal to x squared plus a squared. Again, a is a constant number here. It's any old number at all. What is that going to look like? Well, again, it's going to be a parabola. Z is equal to x squared plus a squared. Again, it won't pass through the point z is equal to 0. Instead, it'll pass through the point z is equal to a squared when x is equal to 1. So what's the slope here? The derivative of z with respect to x is going to be given by 2x. It treats a like a constant, so the derivative of that is 0. So again, I get exactly the same formula, and I can calculate what the slope is at a particular point. For example, x is equal to 1, and I get a slope of 2 times 1 equals to 2. And that's at x is equal to 1. So this is how we can interpret partial derivatives. They're really just the slope of our function in a particular direction, and all other directions are treated as if they're constant, so they can't affect the slope. Now, of course, there's nothing particularly special about x, y, z, and so on. We use those when we're trying to sketch functions in 3 dimensions, but we could look at 7, 23, 49 dimensions if we like. It doesn't matter. So in example 6, we're actually going to deal with a function of 6 different variables. And we're going to ask, what's the partial derivative of this function with respect to just one of those variables? What's the rate of change or the slope of this function of 6 variables in one direction? Now you notice that my function is x1 cubed, x3 to the power 4. That's the first part. It doesn't involve the partial derivative with respect to x to the power x4. It doesn't involve x4, so the derivative here is 0. The derivative of the next piece, again, it doesn't involve x4, so that's going to be equal to 0. So df dx4. First piece is x1 cubed, x3 to the power of 4, doesn't involve x4, so that's 0. x5 over sine x6 doesn't involve x4, so that's 0. I have the natural logarithm, ln, of x4, so that does involve x4, and the derivative of natural logarithm is 1 over x4. And the last term here, minus sine, hyperbolic sine x2 over e to the x1, doesn't involve x4, so my partial derivative doesn't care. So this complicated function actually has a pretty simple expression for its slope or its derivative in the direction x4. So far we've only dealt with functions that have first order derivative, their first partial derivative. But just like with ordinary derivatives, we can define second order derivatives, third order derivatives, and so on. We just have to be a little bit careful because, of course, I could have combinations of derivatives with respect to x and derivatives with respect to y. So let's look at example 7. I've got a function z is equal to x squared sine y plus x cubed y plus y to the power of 5. And I want to find its partial derivatives, including second order partial derivatives. So starting with the first order partial derivatives, the partial derivative of z with respect to x, I can use the subscript z subscript x or z sub 6, z sub x. And again, I'm going to treat y like it's a constant in this calculation because I'm taking the partial derivative with respect to x. So my first term, x squared sine y, I treat the sine y like it's a constant. So I only have to deal with the x squared, and the derivative of x squared is 2x. And I have to include, of course, that sine of y. Next term, x cubed y. Again, I treat y like it's a constant. The derivative of x cubed is 3x squared. And I have that y left over. And the last term, y to the power of 5, well, that's a function of y only. So the derivative of that with respect to x will be 0. My partial derivative of z with respect to y is going to treat x like it's a constant. So in this case, z equals to x squared sine y, that first term is going to treat x squared like it's a constant. So I can just pull that out the front. The partial derivative of sine y with respect to y is cosine of y. The next term is x cubed y. The derivative of that with respect to y treats x like a constant, and the derivative of y is 1. And the last term here, y to the power of 5, doesn't involve x at all. So I have 5y to the power of 4. So the first order derivatives, the partial derivative of z with respect to x and the partial derivative of z with respect to y, those are pretty straightforward. We've already seen how to do that. Now I want to calculate the second order derivative, the partial derivative with respect to z of z with respect to x twice, or d squared z dx squared. So you notice that again we use a very similar notation to the one that we've seen for ordinary derivatives, with the second derivative sign, and we interpret that as being the derivative of the derivative. So the partial derivative of the partial derivative of z with respect to x. The shorthand notation for that is also quite simple. It's just z subscript x x. So two derivatives with respect to x. So the way we're going to calculate this is by keeping in mind what the derivative of x was, the first derivative with respect to x. So that's the first line up here. So we got 2x sine y plus 3x squared y. So the derivative of that with respect to x will be 2 sine y plus derivative of 3x squared is going to be 3 times 2x, or 6x times y. And that's our second derivative with respect to x. I can also calculate what the second derivative is with respect to y. And again, I'm going to do that by taking the derivative of my first derivative with respect to y. So that was given by x squared cosine y plus x cubed plus 5y to the power of 4. I'm going to take the derivative of that with respect to y. So that's going to give me x squared is treated like a constant. The derivative of cosine of y is minus sine of y. So again, I have that factor of x squared still sitting there in front, and I've pulled the minus sign out the front. The next piece is x cubed. I'm going to take the derivative of that with respect to y. That's a function of x only, and so it just becomes a 0. And the last piece is 5y to the power of 4. The derivative of that with respect to y will be 5 times 4y cubed, or 20y cubed. So that's our second derivative with respect to x and our second derivative with respect to y. So far, nothing has been very different from what you've already seen with ordinary derivatives. But now we come to something that is actually new. Because I can take the derivative with respect and take the derivative with respect to y, I can ask things like, what's the derivative with respect to x and y? And to do that, I have to be a little bit careful. I have to ask, which derivative am I taking first? So for example, I could have the derivative of z with respect to x with respect to y, or d squared z dx dy. What I mean by that is it's the x derivative of the y derivative. So I take dz dy and I take the derivative of that with respect to x. The shorthand notation for this is going to be z subscript y subscript x. And the way we interpret that is that the symbol closest to the z is the derivative that acts first. So y is closest to z here, dz dy. So I'm taking the derivative of z with respect to y first, and then I'm taking the derivative with respect to x. So to do that, I'm going to need to go back again and look at what my derivative was with respect to y. So that was given by x squared cosine y x cubed plus 5y to the power of 4. And the derivative of that with respect to x is going to be given by two x cosine y plus 3x squared. And that last part, 5y to the power of 4, that doesn't have a derivative with respect to x because, of course, it's only a function of y. Now that was the first mixed derivative, that is, where I took the derivative with respect to y first, and then I took the derivative with respect to x. But of course I could do the same thing in reverse. I could first of all take the derivative with respect to x, and then take the derivative with respect to y. So let's see what happens when I do that. Again, you notice that I'm going to use shorthand notation zxy, z subscript xy, and again, the letter that's closest to the z goes first. So z subscript xy, I apply x first, so partial derivative with respect to z with respect to x, and then the partial derivative with respect to y. So let's write out what that looks like. So I'm going to take the partial derivative with respect to y of, let's just remind myself what the derivative of z with respect to x was. That was given by 2x sine y plus 3x squared y. So that's 2x sine y plus 3x squared y. And the derivative of that with respect to y is going to be given by 2x cosine of y plus 6. Oops, sorry, I'm taking derivative with respect to y, so that's plus 3x squared. Okay, so let's compare those answers. You notice that in the first case, the first mixed derivative, first of all I took the derivative with respect to y, and then I took the derivative with respect to x, and I ended up with the answer 2x cosine y plus 3x squared. The next case, I did the derivatives in reverse. First of all, I did the derivative with respect to x, and then I took the derivative of that answer with respect to y. And I ended up with exactly the same answer. Now, what you're going to find is that for most well-behaved functions, that's always the case. That if you have a mixed derivative, it doesn't matter what order you take the derivatives in. However, that's not always going to be true, and especially for functions that are discontinuous or otherwise not well behaved, the order of the derivatives does matter. But for most purposes, and certainly for most purposes in this course, mixed derivatives can be taken in any order.